Hello physics students, looking at chapter 8 material today. Chapter 8, we're continuing on with the theme of dynamics. That is talking about force and motion, the causes of motion, and then that leading to how the motion occurs with kinematics and such. But this time we're going on to two-dimensional dynamics. Motion in the plane, not just motion along a straight line. So that's what chapter 8 is about. I know we covered some of this in class already, but I'm going to just start at the beginning in case any of our students weren't able to be in class yesterday. So if you were in class, you can feel free to skip ahead to what we covered. Skip what we covered in class the other day, which was all the way to slide 44. Okay, let's go on. Okay, two dimensions. Let's see here. Let's go to this first problem. This example will introduce us to the two-dimensional aspect of what's going on. All right, example 8.1. Small rocket for gathering weather data has a mass of 30 kilograms and generates 1,500 newtons of thrust. On a windy day, the wind exerts a 20 newton horizontal force on the rocket. If the rocket is launched straight up, what is the shape of its trajectory, and by how much has it been deflected sideways when it reaches a height of 1 kilometer? Because the rocket goes much higher than this, assume there's no significant mass loss during the first 1 kilometer of flight. So if we've got let me do a little free body diagram right here. We've got a force of thrust straight up. That's 1,500 newtons. We've also got gravity going straight toward the center of the earth. And that is going to be the mass times the acceleration of gravity, mg. So 30 times 9.8, which is, that's 294. We've also got a force, a horizontal force. I could draw that to the right or to the left. I'm going to draw it to the right. A horizontal wind force of 20 newtons. Okay, so when that's the case, that means we're going to have an overall force, an overall net force. Which direction is it going to go? Well, the thrust is bigger than gravity, so it's overall net up, but you also got this force to the right. So the overall net force would be something like that. And so the rocket would probably fly something like that in its direction of flight. Alright, so what we're going to do is in two dimensions, we're going to separate things. We're going to break things down into their components vertically and horizontally. Just like we did with kinematics, two-dimensional kinematics. So vertically, what do we have going on? We got the sum of the forces in the y direction being what? We got a 1,500 newton force, and we have a 294 newton force that's going in the negative direction. So positive 1,500, negative 294, and that's the two forces in the y direction. And that is always going to equal, the sum of the forces always equals what? It always equals ma. So in this case, it's going to equal 30, because that's the mass, times the acceleration in the y direction, or the vertical acceleration. Alright, so we can now find the vertical acceleration. So we just do this little arithmetic here. So it's going to be 12 over 6 equals 30. Then divide. I get 40.2 as the acceleration, as the vertical acceleration. Now we can do the same thing for the horizontal direction. Sum of the forces in the x is just going to be what? The only one we've got is the positive 20. That's going to equal ma in the x direction. So that's going to equal to the mass times the acceleration in the x direction. Divide, and we get the horizontal acceleration to be 2/3. Now that we know our accelerations, we can go to kinematics. Alright, so if we go to kinematics, I'm looking for the horizontal displacement, basically. How much has it been deflected sideways? That's what I'm trying to answer. So that's basically the horizontal displacement. So I'm going to start out with my horizontal kinematics to see how far I can get. So a lot of times, we start with A. Let me see what I can do here to give myself more room. So got more room now. A x equals 2/3. So then velocity in the x direction, final velocity is equal to what? It is the antiderivative of that, which is 2/3 t plus v0, v0 being, we can say 0 in this case. And then the final position is the antiderivative of that, which is going to be 2/3 t squared over 2. So 2/3 divided by 2 is 1/3. So 1/3 t squared plus initial position, or x0, which we could say that is also 0. So it's just that. So now we know if we want to find the final horizontal position, then what do we need to know? We need to know the time. How can we know the time? Let's go over to the vertical side and see if that can provide that time for us. Okay, so a sub y equals 40.2. So v sub y final will be the antiderivative of that, 40.2 t plus initial vertical velocity, which we could say is 0. Then the final vertical position is going to be the antiderivative of that, which is going to be 40.2 t squared over 2, which is 20.1 t squared plus initial vertical position, which we can say is 0. So now I have a final vertical position and a time variable. Is there one of those that may be known? And it actually is, because look, the question said, how much has it been deflected sideways when it reaches a height of 1 kilometer? So there's my vertical position that I can plug into y, 1 kilometer. Now don't plug in 1, that's the tricky part, right? Because it's talking about kilometers where we are dealing with meters in these equations. So I'm not plugging 1, I'm going to plug in 1,000 for YF, and then do a little algebra, divide by 20.1, take the square root, and we can find the time that way. Let me go ahead and do it in my calculator. I get 7.05. So now I know my time. I come back over to the horizontal side to find what I'm looking for the answer to the problem. 1/3 times 7.05 squared. And so now XF equals, let me do this in my calculator, squared by 3, 16.58. And that is my final answer. That will be in meters. So coming back here to the PowerPoint and if you can barely see it there, they say that the answer is 17 meters, which is what we got, 16.58. All right. Some of this is going to be review, projectile motion review. So with projectile motion, remember, is when something is launched and then the only force on that thing from then on out is just gravity. And the force of gravity is always equal to negative mg. So yeah. Now, remember, we covered this also before. If you launch something from the ground, you get a maximum range, meaning the thing will land at the farthest away by a 45 degree, launching it from a 45-degree angle. That will provide the maximum range. All right, but now all of these kind of paths are neglecting drag force. They're neglecting air resistance. Look at this next slide. When there is air resistance, now look at the path. The air resistance is happening to this thing the whole time, and it kind of makes it not a symmetrical parabolic shape anymore. The fact that it's going to be going slower and slower and slower horizontally because of that drag force makes it no longer symmetrical, which then makes the maximum range occur at something less than 45 degrees. In this particular drawing, it's at 30 degrees, but it's not necessarily 30 degrees. It depends on what the drag force is. So, but it's always going to be something less than 45 degrees. So, like when I'm playing golf, and there's a very windy day, and the wind is in my face, meaning it's blowing against me, I want to keep the ball lower than I normally do so that the ball will go further so that the wind won't affect it as much. Uniform circular motion, another review. Remember, in uniform circular motion, we have no acceleration that is making it go faster or slower around the circle. It's maintaining a constant speed. However, there is an acceleration. There is an overall acceleration because it's constantly changing directions. So velocity is not changing its magnitude, but it is changing its direction, which means there has to be an acceleration to make that velocity change direction. And it is what we call a centripetal acceleration. That means center-loving acceleration. So it points toward the center. And this centripetal acceleration, remember, is not some new vague acceleration. It's always caused by some force that we're already familiar with. Something like gravity, or tension, or friction. Something is pulling that object toward the center of a curved or circular path to cause that centripetal acceleration. We have linear velocity, which the synonym for that is tangential velocity. Let me draw that for you. So as an object is going around a circle, all right, something's holding that object. So something is holding that object toward the center. It has this acceleration toward the center of the circle. It has a tangential velocity. That the tangential velocity is always pointing tangent to the circle. It's the direction that the object would go if all of a sudden the centripetal force was no longer there. Like if the rope snaps or something, then the object is going to now go in a straight line. the tangential velocity, you also have what's called an angular velocity. So this is the tangential velocity, or you could call it linear velocity, because it's the velocity in a straight line. But there's also what we might call an angular velocity, which we represent with the Greek letter omega. You remember, we got A, V, and X, or S, or Y, or whatever, for position in the linear direction. Well, in the circular motion, in angular concepts, what we have symbols that kind of match up with those. We have alpha for angular acceleration, we have omega for angular velocity, and we have theta for angular position. And to get from circular to linear, we can always take the rotational or circular. When I say rotational, I mean circular. The rotational concept, multiply it by r, which is the radius, and that will always give us the linear version of that. So if we want velocity, omega r gives us velocity. Theta r gives us position, or displacement, or whatever you want to say. So, and this is all having to do with the angle. Like omega is the rate of change of the angle. How fast is the angle changing? Acceleration, alpha, is the rate of change of omega. Theta is the angular position. So it might be like 90 degrees or 160 degrees, or we might do in radians. It might be at 3 pi over 2. That's where the angle is. All right, now this centripetal acceleration, which we might call the radial, we can call it centripetal, or we could call it radial acceleration. All right, the radial acceleration, and I call it radial because it points in the direction of the radius toward the center of the circle, is always equal, and you may want to just take good mental note of this, it's always equal to v squared over r. So the linear or tangential velocity squared divided by the radius, that will give us the centripetal acceleration. And it's also equal to omega squared r. So either one of these can give us the radial acceleration. All right. Now, here's something new for us. This is going to be probably feel a little weird to you. At first, but when we're dealing with circular motion, when an object is going around the circle, okay, normally we deal with x and y coordinates, or maybe even x, y, and z coordinates. When we're dealing with circular motion, we're going to deal in what's called r, t, z coordinates. And these are kind of like, these are circular coordinates. So that it's not XYZ plane, it's the RTZ plane, and it's going to be very strange at first. But it really helps us do physics. It's very helpful in figuring out physics problems once you get used to it. The r-axis always points toward the center of the circle. This is the r-axis. Okay? It always points toward the center of the circle. And the r-axis, the positive r-axis, always points toward the center of the circle. So in this case, the positive r-axis is going in the direction of that arrow. The negative r-axis would be pointing away from the center of the circle. So if we're over here, the positive r-axis, not very good at drawing it, is pointing this way. That's the positive r-axis. The negative r-axis would be pointing that way. Alright, the t-axis is the tangential axis. It always points in the tangential direction. and the positive tangential direction, positive t, is always going to be the counterclockwise tangential direction. So this is going counterclockwise. So this is positive. Negative would be in the clockwise. So this would be the negative t direction. So over here, positive t would point this way. Negative t would point that way. And the z-axis is coming straight out from the paper or the board or whatever. In this case, your computer screen or phone screen. The z-axis is pointing straight out. That's the positive z-axis. The negative z-axis would be pointing straight into the paper. So it's like imagine we're looking down on a racetrack, a circular racetrack, and a race car is going around this racetrack. All right, the tangential velocity is that, or the tangential axis is that. The radial axis points toward the center of the circle, and the z-axis is coming out at you. So you're looking down on it, so it's pointing up toward you, toward your perspective. If we drew it, we could draw this in a different way. If we think about it like, you could draw it like this, where, let's say this is pointing toward the center of the circle, so that's the radius. This is pointing toward the tangent, something tangent to the circle. So imagine something's going like that around the circle. This is the t-axis, and this is the z-axis. Hopefully you can see that as a three-dimensional drawing. Yeah, so maybe it's a right angle right there. That's a right angle right there. This is a right angle right here. So it's like you want to draw a three-dimensional box. We would draw it like this. I'm just helping you to see the three dimensions. Okay. The origin is actually the object. This is the origin. So the origin is actually constantly moving. And R, T, and Z are also, at least R and T, are constantly changing directions. Because R is always pointing toward the center of the circle, T is always pointing tangent to the circle. Alright, we'll get used to that, and maybe you can learn to love it. Alright, notice on this diagram, this is like, imagine you're looking at the back of the race car. Okay, we are looking, like this dot represents the bumper or the rear end of the race car. And it's going away from us. It's going into the page. When that's the case, the z-axis is pointing straight up. It's pointing like that. The r-axis is pointing, positive r-axis is pointing to the left here. And the t-axis is actually coming out of the page toward you. If we're looking at the rear end of it, then the positive t would actually be going into the page, and the negative t would be coming out of the page. All right. Quick check 8.1. All right, this diagram shows 3 points of a motion diagram. Particle changes direction, but with no change of speed. What is the acceleration at point 2? All right, so this takes us back to way earlier in our year together. Do you remember how to find acceleration vector using velocity vectors? Acceleration is always equal to VF minus VI. change in velocity, but that's also over t, over the change in time. But we have no change in time, but we don't really need it to at least get the direction of acceleration. We would maybe not know the size of it, but we would at least know the direction of it by doing that. So this is the same thing as Vf plus negative Vi. So you in other words, here's Vi, here's Vf. So you take Vf and you add the negative or opposite of Vi. So we imagine flipping that Vi in the opposite direction and adding it now to Vf, so that now Vf plus negative Vi will be something like that. And so A now is going to be start at the beginning of Vf and end at the end of Vi with this addition. So here's A. So it is choice B. So now what this is trying to get you to see is, imagine this is circular motion, okay? It's a very, very large circle that I can't fit in my screen, but imagine this is circular motion. So the A at every point is always going to be pointing toward the center of that circular motion. Okay. Quick check 8.2. A toy car moves around a circular track at constant speed. It suddenly doubles its speed, a change of factor of 2. So that's what double means. As a result, the centripetal acceleration changes by a factor of what? So when it doubles its speed, alright, so this is where we need to remember that centripetal acceleration, we can call it that, or we can call it that, centripetal or radial, whichever one you want to call it, is equal to v squared over r, that's the tangential, or omega squared r. So in other words, if we double our speed, that means we're doubling v, or we're doubling omega. So if we double the v or double the omega, imagine plugging a 2 in for v or a 2 in for omega. What is that going to do to A? Well, it's going to square the 2, which is going to change A by a factor of 4. So 4 would be the answer here. Okay. Dynamics of uniform circular motion. An object in uniform circular motion is not traveling at a constant velocity in a straight line. Consequently, the particle must have a net force acting on it. The net force is this. It's ma. A being centripetal acceleration, or radial acceleration, which is going to equal m, instead of ma, you could write mv squared over r, or you could also write m omega squared r. Either way, because v squared over r and omega squared r are equal to a. Without such a force, the object would move off in a straight line tangent to the circle. The car would end up in the ditch. Alright, so in NASCAR, they bank these curves so that it increases the centripetal acceleration or centripetal force, so that it helps the cars not slide and go off in a straight line. It helps them to make that curve. Alright, this is just the RTZ stuff. The net force points in the positive R direction all the time. Okay? The z-axis is out of the page on this diagram. We're looking down on this situation. The tangential velocity is always going to be tangent to the circle. Okay. Quick check 8.3. An ice hockey puck is tied by a string to a stake in the ice. The puck is then swung in a circle. What force or forces does the puck feel? Okay, so this thing is tied to the stake and it's moving in a circle. Does it feel a new force called the centripetal force, a new force called the centrifugal force, one or more of our familiar forces pushing outward, one or more of our familiar forces pushing inward, or you have no clue. Alright. It's not a new force. The centripetal force is not some new force. It's always caused by something we've already talked about, like tension or gravity or friction or something like that. It's not the centrifugal force. Centrifugal force is kind of an imaginary force. It's the force that you imagine or you feel like is going on when you're going in a circle, when you're going around a curve. It's because it feels like you're being forced or thrown outward. But that's really because your body wants to continue in a straight line, whereas whatever object you're inside of is going around a curve. So and what keeps you going around the curve also, along with your car you're inside of, is your seat belt or the friction between you and the seat or the car door itself. So the friction between the tires and the road are causing the car to go in a circle. It's pulling toward the center when that's the case. And then whatever is attaching you to the car is also pulling you in the same direction. Even though you feel like you're being flung outward, that's just really an imaginary thing that you're feeling, but not what's really happening. So what's going on with the puck is it's feeling one or more of the familiar forces that's pulling it inward. Alright, an ice hockey puck. And this is now, we've made it to how far we made it in class yesterday. So I think what I'll do is I'll stop it right here so that you guys who were in class can start on the next video.